carnival? Okay. How many of you have been to a carnival and played one of their games? Did you win? Anybody win? Yeah, you won? Okay, how many times did it take you to win?
A lot.
Okay. Carnival games are set up to do what? Be rigged. Okay. Okay, they want to take your money, right? Okay. Well, there's actually math behind that, and that's what we're going to look at today. And that's actually what you're going to use for your game day project starting on Thursday. Okay? Sorry. So go ahead and turn it to the back side. Whoa. That's where the notes are. Okay. So any sort of game that we play, not based on skill, has certain probabilities of things occurring. Okay, so have you ever pick up the duck, and if there's something on the bottom, then you win. Okay, or drawing a card, a casino situation. Some of you are familiar with some casino type games, even though you would not have gone to a casino. Post prom, they have casino games at post prom, right? Okay. Okay. So those of you who are juniors this year will be experiencing post prom maybe this year. Okay. But there are certain probabilities of winning. There's certain probabilities of losing. You could even have a situation where you break even. So you bet $1 and then you get the dollar back. You break even. Okay. So what mathematical expectation is we calculate what we are expected to win or what we are expected to lose. It's one number that describes what should happen every time with the game. Okay? So what we're going to do, we are going to set up a probability distribution where we take, what's the probability of winning, what's the probability of losing, and we're going to attach a value to that. So maybe we're going to lose $1, but if we win $5. And so then those are going to be multiplied to their respective probabilities, and added together is what we call our mathematical expectation. What is the expectation every time we step up to this game? Is the dealer expected to win? Is the player expected to win or lose? Okay? If you're making a game that a carnival or casino will put into place, would you want a mathematical expectation where the dealer wins or loses money? Wins money, which means over time the player is going to lose money. Now, is there a chance for the player to win every now and again? Yes. But the more you play, the more it's going to average out to the player losing over time. Okay, and we'll kind of talk more about that as we go. So we have two examples that we're going to go through. Okay, go ahead and read through example number 1 about roulette. Okay, so what's my sample space? What are we concerned about? Numbers or colors? We're concerned about colors. Now there's a lot of different ways to bet and play roulette. We're just gonna think of betting on a color. Okay, because you can bet on numbers. We're just gonna talk about betting on a color. Okay, so there's no numbers. We're gonna pretend. Okay. What different colors do we have?
Red, green.
We have red, we have green, and we have black. Okay. Now, how many reds are there?
36. Or no.
18. There's 2 greens, right? and there's 18 black. I don't really want to write the word red 18 times, and I don't really want to write the word black 18 times. But at least we have an idea of we have, 38 different options up there? Okay. All right, so what's the probability of winning? What color do we want for us to win? We want red. How many reds are there?
18.
Okay, so there's an 18 out of 38 probability of winning. And the probability of losing,
36. 18 out of 36.
actually 38. Because there's 18
Oh yeah, because of the two greens.
because of the
My
two
bad.
greens. Okay? Now, losing would be considered everything else, right? It's either you win or lose. There's nothing in between. So we have a 20 out of 38 chance for losing. Okay. So this is what we're going to do. We're going to create a probability distribution. With each probability and its value. Okay, so what would the value be for 18 out of 38? What are we going to put up here as our value? Madeline, what are we winning when we win? You're walking away with $2 more than when you started? Okay, you're walking back with an additional $1. So the dollar you placed down, you get it back, and an additional $1. So you're only up $1. Like the dollar you placed on the table is now back in your pocket plus one more. So you're walking away with only one more than when you started. Okay? If you lose, Jacob, what's true about our wallet when we walk away after losing? We're down $1. Okay? We got to think about, putting money back into your wallet. How does it compare to when you started? Okay, we're down $1 if we lose. Okay? So if I ask you for the mathematical expectation, we are going to take each probability and multiply it times the value. So I'm going to take 18 out of 38 and multiply it by a positive 1. Okay? And then I'm going to do that with 20 out of 38. I'm going to multiply that by a negative 1. And each of those are going to be added together. If I had 5 different ways of winning or losing, we would do this 5 times. What's our mathematical expectation?
You want in decimal or fraction?
Give it to me as a fraction first, Nathan.
Reduced fraction is negative 1 over 19.
Okay, so you got negative 2 over 38, which you reduced to negative 1 over 19.
Yeah.
Okay? As a fraction, negative point, give me like 4 decimal places.
0.526.
Okay.
Which way do you want it
I'm really okay either way. Okay? Now, when we get to number 6, we'll get there. Now, actually, I'm going to take a step back. Well, I kind of want to see both. How's that? Because we are talking about money, and so decimals kind of make more sense. But I want you to keep this in your calculator, okay? So negative 1 over 19 is negative 0.0526. What does this mean? Every time I step up to play roulette and bet on red, I can expect to lose a nickel every time. Now, am I going to literally lose a nickel every time? No, but if I keep playing, I'm going to win some, and I'm going to lose some, and it is going to even out to where I'm losing a nickel every time. Okay? Okay, what does this mean for the house? What's happening for the dealer? They're making a nickel every time somebody plays. So they aren't literally making a nickel every time because they're collecting dollars or giving out dollars. But every time somebody bets $1 on red, if that happens over and over and over and over and over, each time they're making a nickel. Okay? Let's look at number 6. If we played this game 100 times, how much money would we expect to win or lose? Okay? How are we going to calculate that? What do we do?
Would you just put the 100 in for probability?
No, we need to do something with this number. Like the probabilities are going to stay there. Okay, Reagan, what should we do with this number right here?
Multiply it by 100.
Okay, if we take this and we multiply it by 100, so like that negative 1/19th, and multiply it by 100, we are going to lose $5.26 over the course of 100 plays. No, that's not so bad, right? I play 100 times and lose $5. Okay, it could be a lot worse, but that's the expectation. Now, as a dealer, what's happening with the dealer when somebody plays this game 100 times? They're winning. They're making $5.26. Okay? Now, something that you need to kind of start thinking about is you get to create a game. And your game, you get to have the control over if your mathematical expectation is positive or negative, and how big that positive or negative number is. Okay? You also get to answer the question for me, would a casino buy your game? Okay, so let's kind of start thinking about that. If you run a casino and somebody presents you this game where a 100 times it's making $5, what are you thinking as a casino owner? Is that enough money for you?
Well, if you
Is that
play
kind of what
100
you're thinking?
Yeah, if you play 100 times, then they win $100.
Well, in this case, if they play 100 times, the dealer's making $5.26.
Yeah, but aren't they making money each time?
They're making positive 0.05 each time. Like whatever it is for the player, it's just opposite for the house.
So, I'm confused. Would it be a good investment or not?
Well, and that's something you get to decide in your project. Okay, some of you may say that this isn't worth the effort. It's only $5 over 100 times. Okay, those are things that you can kind of talk about. Or maybe you think it would be okay because even though we're not making a lot of money, it's not a lot of effort to run the game. Okay, I don't know. It's something that you'll get to answer in your reflection next week. But I just want to kind of start getting the wheels turning. Okay? Now, roulette is a much more complicated game than this, but this would be the scenario if we were just to bet on red every time. Okay? All right, go ahead and read through example number 2. Okay. So, what's happening? We have envelopes, right? We have 6 $1 envelopes. we have 2 $5 envelopes, 1 $10 and 1 $20 envelope. Okay, so here's my sample space. How many envelopes do we have? We have 10 envelopes. Okay, this probability is pretty straightforward. Okay, in this example, our probability is not going to be difficult to figure out. We have a little bit more work to do with our mathematical expectation. Okay, so the probability of winning. Is there more than one way to win? Yes. We have a 1 out of 10 chance of winning with our $10 bill. And we have a 1 out of chance to win with our $20 bill. So total, there is a 2 out of 10 chance for winning, but we can do it in 2 different ways, and we'll come back to that here in a moment. Okay. Now, if it costs $5 to play the game, Kelly, how many ways can we lose?
8. Like it'd be 8 times.
Okay, I disagree with you. If it takes $5,
I guess you could break even. But
okay, so if you pay $5 and you get $5, are you losing money?
No.
Technically, no. Okay, so I
Yeah.
tricked you. Okay, so how many ways instead would we lose?
6.
Okay, so there's actually only a 6 out of 10 chance of losing because there's 2 ways where we break even. Okay? Yes.
Where does the second 1 out of 10 come
So there's one way to get a $10 bill and one way to get a $20 bill.
from? Why wouldn't 5 be? Oh, because they're paying 5.
Yes. Yes. Okay, so we'll make our probability distribution. How many different numeric columns are we going to need for this probability distribution?
3.
I'm hearing 4. We need 4 different columns because there are 4 different amounts of money we could win, lose, or break even. Okay? We have a 6 out of 10 chance of getting that $1 bill envelope. Our wallet is different by how much? We are down $4 when we walk away from that scenario. Okay? Hey, we got $1, but we also paid $5, right? Okay, you have a 2 out of 10 chance of getting the $5 bill envelope. And if you get a $5 bill envelope, then your wallet is the same, right? You paid 5, you got 5. So you break even. Okay. You have a 1 out of 10 chance of drawing the $10 bill envelope. And if you pay $5, you walk away with 10, then your wallet is different by plus 5. Okay? And then last but not least, you have a 1 out of 10 chance for winning the $20 bill. And your wallet would be different by how many dollars? Plus 15. You pay 5, but you get 20. Okay? Now, some of you may think, well, I have a 10% chance of walking away with 15 extra dollars in my pocket. Okay? And that's very enticing, isn't it? Okay? And if I don't get that, I could at least break even. Okay? Let's calculate this mathematical expectation. Okay? So our mathematical expectation, we are going to take the value times the probability plus the value times the probability. value times the probability, value times the probability. Like you wouldn't need to actually put it in there. Yeah. 0 times 2/10 is going to go to 0. So whether you write it or not is up to you. What do we get for our mathematical expectation?
$2.40.
Maybe go back and look at your calculator. I don't think it's that big. Did you find a mistake? Yeah. Okay. Because this is negative 24/10 plus 0 plus 5/10 plus 15/10, which means we're left with negative 4/10, right? Or negative 0.4. Every time you as a player play this game, you are expected to win or lose. Lose 46. If you were running this game, you as the dealer, every time somebody plays, would expect to win 40 cents every game. Okay? You as a player really like this game and you play it 100 times. You play this game 100 times. Sophie, what's going to happen? You're going to lose $40. Because we're going to take our negative mathematical expectation and multiply it by 100. But hey, if you're the dealer, you're winning $40 after 100 times. And that's pretty cool. Okay. Now, I want to make a comment about the probability distribution. What's true about this row right here? What does it add up to be? It adds up to be 1 because it's all of the probabilities. I know that this has a value of 0, but I still need to see it in your probability distribution. I'm fine with, you know, if you leave it off down here because, 0 times anything is 0. But in your table, I better see that your probabilities add up to be 1. And that's something that's going to be very important Thursday, Friday, when you're coming up with your game and you're figuring out all the probabilities. The probability of all the possibilities do need to add up to be 1. Okay? Okay, so where's this going? You're going to create a game. And what we're going to do is we're going to figure out what the mathematical expectation is of your game. Then we're going to play each other's games with Tootsie Rolls. And then we're going to see what we calculated to happen. Does it match the data that we collected? Okay? That's how we're going to put all of this together. Okay? Now, I need to point some things out on your homework assignment. I would like you to please read through low, lower, lowest. So first of all, for all 5 of these games, I want you to assume that we are wagering $1. Okay? We are going to wager $1. And that's what's going to happen Thursday. You're going to create games that cost 1 Tootsie Roll. Okay? Now, do you see where it says the payoff is equal to the amount wagered? If you win and the payoff is equal to the amount wagered, what would be the value in your distribution? What do you say? Plus 1, okay? If the payoff is equal, you place your dollar down. The dealer doesn't take it unless you lose. So you place the dollar down on the table. If you win, they grab a dollar from their pile and give it to you, and now you're up $1. Does that make sense? Okay. So we have about 8 minutes left in class. What I would love is for you to set up your first game. So you have 5 games in which you need to answer the first 6 questions for. And then after you've done all 5 problems, then 7 through 10 are asking you to compare the games. Okay, so go ahead and before you leave, set up low, lower, and lowest, and see if you can get those 1 through 6 questions answered before you leave. Okay? For your sample space, if you need a tree diagram, draw it. Or write out all the possibilities.